everyone, and welcome back. Today, we're going to start 2D kinematics, and we are actually only going to deal with a subset of 2D kinematics called projectile motion. And the reason why we're sticking with projectile motion for now is because that is the only kind of 2D kinematics that the AP1 exam actually deals with. However, that being said, the technique I'm about to teach you can be used for any type of 2D kinematics problem. So for anyone who's actually interested in going to AP Physics 2, this is definitely a technique you're going to want to be familiar with. All right, as you can see, I have our kinematic equations on the screen. However, considering they're in the way, I am going to take them, make them small, and stick them in the corner of the screen here so we can use them a little later. All right, now let's bring up a visual and have a little discussion. Okay, so here is your basic projectile. I have a ball being fired out of a cannon. You see it flying through the air, and it hits the ground. Even with this simple representation, you could probably see there's going to be some symmetry here. Now let me show you the same situation. However, this time I'm going to put a velocity vector on the ball. So here's my velocity vector. As you can see, the velocity vector starts large. As the ball rises in the air, it changes direction, gets smaller because the ball slows down as it rises in the air. Then as it falls back toward the ground, the velocity vector changes direction again and gets larger because the velocity of the ball is increasing as it moves toward the ground. Now this next one's going to be the important one. Instead of having this single velocity vector, since that velocity vector for most of this is at an angle, we are going to break it up. Because, as I've stated earlier, anytime there's a vector in this class at an angle to your axis, you are always going to break it up. So here it is. Now we have our projectile moving along its arc, and now you can see the y-axis and x-axis velocities independently. So first, take a look at the y-axis. Notice on the y-axis, the velocity starts large and upward because the ball is being fired up into the air. It is getting smaller. At the very top, if you notice something special, on the y-axis only, the ball comes to a stop for a moment and then increases its velocity back down toward the ground. And you can see that because the velocity vector points downward, it gets larger and larger and larger. In other words, if you took this ball and threw it straight up in the air, this is exactly what the y velocity vector would do. It would be large upward, get smaller, smaller, smaller. It would disappear because at the very top of the throw, the ball would come to a stop, and then it would start falling toward the ground and speed up as it fell toward the ground. We actually did a problem with that exact situation not too long ago, where I threw an apple or a ball straight up into the air. Now, here's the important addition here. Take a look at the velocity vector on the x-axis. What is it doing? It is doing nothing. It is not changing in the slightest. This is very important. The velocity vector on the x-axis is not changing at all. Why? Well, let me change our visual here. Instead of velocity vectors, I'm going to put a force vector. So literally, we're going to turn this into a force diagram. So let me remove the velocities and put in a force vector. And notice what direction the force vector is in. The force vector is always pointing down. Why? Well, keep in mind, we're ignoring any type of air resistance. So, what is the only force exerted on the ball? The only force being exerted on the ball is force Earth. And Earth is pulling the ball downward, negative y-axis. There are no forces to the left or right. There are no forces on the x-axis at all. And if there are no forces on the x-axis, that means there is no acceleration on the x-axis, which means there is no change in velocity on the x-axis. So the velocity on the x-axis does not change. On the y-axis, there's a constant force downward. So if I change our visual from force to acceleration, what direction is the acceleration going to be in? Ta-da! The acceleration is downward because the acceleration is always in the same direction as the net force. So if you notice, Newton's first two laws act independently on each axis. On the x-axis, there is zero net force. Therefore, there is zero acceleration. That's first law. On the y-axis, there is a force downward. Therefore, there is an acceleration downward. That is also first law. On the y-axis, since acceleration is net force divided by mass, the acceleration downward is a constant value, because if you double the mass, you double the net force. That is Newton's second law. So these laws apply independently on the axes. So for our last visual, if I put it all together, net force is downward, therefore acceleration is downward. Therefore, we have a change in velocity on the y-axis, but we do not have a change in velocity on the x-axis. In short, and this is the big takeaway, the axes are treated independently. You are either dealing with one or dealing with the other, but you're almost never dealing with both at the same time. So, that being said, let me introduce you to what is probably the most basic of projectile problems. So here's our problem. A marble moving at 3 meters a second rolls horizontally off a 1.8 meter high table and hits the floor. How much time does it take to hit the floor? How far horizontally did it travel? And what is its velocity when it hits the floor? Okay, so this is how you solve any 2D kinematics problem. Watch carefully. There are 4 steps. 1, you will draw the arc. Here's my table. Here's the ball. Rolls off the table, goes down, hits the floor. This is all you need, a quick sketch of the arc. I label my initial point and my final point. Step 2, break up your initial velocity vector. In this case, my initial velocity was directly to the right, so there's nothing to break up. My initial velocity is exactly one of my axes, so I do not have to break this up into its x and y components. Okay, step 3 is the really important one. If you recognize that you're dealing with a 2-dimensional kinematics problem, the next thing that goes on the page is this table. Take a quick look at it. Do you recognize what you're looking at? VI, VF, acceleration, displacement. These are the kinematic givens split into the x and y components. This table is extremely important because, as I said before, you're either working in the x or you're working in the y, but you are never working in both at the same time. If you notice, one of the variables is also missing. That variable is time, and time belongs here. Time does not belong in either of these columns, it belongs in the center. Why? Well, if you notice, all these other variables are vectors, which means they have a direction, which means in turn, we can actually split these into x and y components, velocity, acceleration, displacement. Time, however, is a scalar. It does not have a direction. Therefore, it is the only variable that belongs in both columns at the same time, which is why I put it in the center. Now, here's what that means. Typically, you need to find information in both columns. And what usually happens is you get good information in one column and you need to jump to the other. How do you do that? Well, time is your bridge. In other words, what nearly always happens is that you get good information in one column. In order to jump to the other column, you need time to get to the other column. Because as a reminder, in general with kinematics, you need 3 good pieces of information to solve for anything else. So, long story short, you're either working in one column or you're working in the other column, and in order to jump from one column to the other, you need time as your bridge. Okay, while we're here, we're going to start filling this in, because this is literally listing our givens. And if any of the givens are off, then the whole problem is going to be off. But before I do that, there's actually one thing I can do here. Looking at my diagram, I can actually go through this table and find out if anything is negative right now. And this is actually a good skill to know. If I look on the x-axis, my velocity is to the right. So my initial velocity is going to be positive. My final velocity is also going to be positive because it's still moving to the right. Acceleration on the x we'll talk about in a second. Displacement on the x-axis is to the right, so that is also positive. On the y-axis, VIY we'll talk about in a second. VFY, the marble is hitting the ground. It is going downward when it hits the ground, so VFY is definitely going to be negative. Acceleration on the y-axis, you know what, I'm going to put that in right now because we already know it. This object is in free fall. What is the acceleration due to Earth's gravitational pull? We just did this recently. It is negative 9.8 meters per second squared. So I'm going to put that in right now. My delta y, the ball is going from up on the table down to the floor. So my displacement on the y is also going to be negative. If I put those signs in right now, it ensures that I don't make a mistake later concerning them. So it's a good idea to do that before you even put in any numbers. And your little projectile arc diagram tells you exactly what's going to be positive or negative in this table. That's why it's important to create. Okay, so let's actually fill in the rest of some givens here. A marble is moving at 3 meters a second, rolls horizontally. Okay, this word. So we know a table is flat, but I put this word here on purpose because it is very descriptive. Horizontally means this velocity is entirely on the x-axis, which means 3 meters a second is my VIX, 3.0 meters per second. Now, if it's moving horizontally, what's the initial velocity on the y? Well, if it's rolling horizontally, looking at number 2 here, my initial velocity vector, there is no velocity on the y-axis, 0 meters per second. So on the y-axis, it has a 0 initial velocity. I'm going to keep going on the x table here. Let's jump to acceleration on the x. As I showed you with our visual before, if there is no net force on the x, there is no acceleration on the x. So acceleration on the x is 0 meters per second squared. And the definition of acceleration is a change in velocity over a period of time. So if there is no acceleration, there is no change in velocity, which means my velocity final x is also 3.0 meters per second. I do not know delta x. I do not know how much time it takes to hit the floor. We already did VIY. We do not know what the final velocity is on the y when it hits the floor. We already put in the acceleration on the y because it's due to gravitational pull. Delta y. Do we know delta y? Well, yes, we do. The table is 1.8 meters high. Therefore, the marble falls negative 1.8 meters in order to hit the floor. So in other words, vertically from my initial point to my final point is 1.8 meters downward. Okay, so we have a total of 9 listed givens, and we just found 6 of them, which is pretty good. And believe it or not, listing these givens is the hardest part of the problem. Seeing if you fully understand the initial situation is probably the toughest part of a physics problem. If you can get to this point, then the rest is literally just a puzzle. Here's the deal. We have these values. The goal of the puzzle is to fill in the missing values. So we're missing 3 of them, VFY, time, and delta x. And as I said before, you're either working in the x or you're working in the y, but you're not working in both. So let's see which column has better information. First, I'll check out the x. I have VIX, VFX, and AX, but AX is 0, which immediately removes the acceleration formula here. I don't have displacement or time, so this one's no good. The first one, I don't have displacement or time, so this is no good either. And this last equation isn't telling me anything I don't already know. Acceleration is 0, so this part would cancel. VI squared equals VF squared, but I already know that because they're the same value. So the x-axis is not allowing me to actually find anything. Let's take a look at the y-axis. Y-axis, I have VIY is 0, I have acceleration on the y, and delta y, and they're all different values. What could I find pretty easily? Well, if I have acceleration, displacement, and VI, I can use this fourth equation. So let's use this one, because the only thing missing is VF. I will rearrange that, VI squared plus 2a delta d equals. This first part's 0, plus 2 acceleration, negative 9.8 meters per second squared. Delta d is negative 1.8 meters. These 2 negatives will cancel, which is good because I'm under a radical. And I will get positive negative 4.2 meters per second. And remember, we've already decided this value has to be negative. So I'm just going to erase the positive here. I'm going to take that and immediately put it in my givens list. Negative 4.2 meters per second. Okay, now that we have the entire y-axis, I can very easily get my bridge, which is time. I'm going to use the second kinematic equation here. VF minus VI over A is negative 4.2 meters per second minus 0 over negative 9.8 meters per second squared. These negatives cancel. I get a time of 0.449 seconds. Again, I'm going to take that and immediately put it in my givens, 0.449 seconds. Now that I have my bridge, I can jump to the x-axis. And now finally, it is time for the third kinematics equation, time to shine, because the acceleration on the x-axis is 0, which means I will use this. The entire right side of this equation cancels, and I have delta x equals VIX times time. And notice I'm identifying it for the specific axis, which actually is something I should have done here. So since I'm working on a specific axis, my variable should represent that as well, because someone looking through my work, including myself, should very easily tell if I'm working on the y-axis or the x-axis. So VIX is 3.0 meters per second times my time, which is 0.449 seconds, gives me 1.35 meters. So delta x is 1.35 meters. So I haven't even looked at the questions in a while. Once I set up this table, my next goal was just to fill everything in. So let's take a quick look at the questions. How much time does it take to hit the floor? Found it right here. How far horizontally did it travel? Got it, right here, it's my delta x. What was its velocity when it hits the floor? That we still need to find, because when it hits the floor, it is not just going straight down, it is going down and to the right. So to answer this final question, I'm going to use these two variables, vfx and vfy. It's velocity on the x-axis and velocity on the y-axis when it hits the floor. And this is vector addition. So velocity final x is to the right. That is 3.0 meters per second. Velocity final y is downward. That is 4.2 meters per second. I am letting the arrow speak direction, which is why this is not negative. The final velocity is this way with this angle. So using Pythagorean's theorem, this vector here is 12.6 meters per second. In order to find theta, I will do inverse tangent of 4.2 divided by 3, which will give me 54.5 degrees, which means the final velocity of this marble will be 12.6 meters per second at 54.5 degrees below the positive x-axis. This is the final velocity of the marble. This is the time it took to hit the ground. And this is how far it moved on the horizontal before it hit the ground. Combining the final velocities is my fourth step. Now, all of this may not be asked for, but this technique solves for pretty much anything you could be asked for. They may ask you simply for the time or simply for delta x. But if you use this technique, there's pretty much nothing they can ask for that you will not be able to find. This encompasses everything. Draw your arc, label initial and final points. Break up your initial velocity vector. We'll be doing one in my next video that actually does this 2 dimensions. 3, and the most important part, make a table for the x and y axes. Time is in the center. List in any givens you can get from the problem. Solve for anything that you do not have using kinematic formulas. And 4th, if you need to, in order to find the final velocity of the object, combine your final velocity vectors using vector addition and then state it. If you notice, this uses a lot of our previous skills, and those skills will continue to be put to use. Okay, I'll end this here. Have a good day. This is Mr. M, signing off.